All right, I think we're ready. Today we're just doing a little bit of SolidWorks demo, and then if there show up any questions in the chat, we'll see if we can address those. Tomorrow is the exam, so we won't actually meet on Zoom. I mean, we will meet on Zoom. We won't meet here. Why don't we jump into the? Actually, first let me go over here and make sure you know that class 2. There's some practice stuff and an outline. Well, actually not that one. Where's the outline? Section summary, practice. I know I put made an outline. There it is. I actually put that exam outline. Maybe we should put that in the same class as the exam. Let's do that. There we go. There's the exam outline, so you can kind of get an idea of what is going to be on the exam. So all of that's in class 22, so you can look at it there. All right, but today what we're doing, let's see, can we do a machine question? Yeah, if you see one, maybe look through the web work and one that looks interesting, and we can do a machine thing once we do our after we do our SolidWorks. So since we're not doing like you go to the lab, physical place, and do a test, we've been replacing the labs with SolidWorks. I know some people are having trouble, getting SolidWorks. Either they don't have it or the virtual machines aren't working or whatever. If you end up in one of those situations and you just can't get SolidWorks to work on your own computer, what you'll do is you'll follow the video that goes along with the lab where I do the demonstration, and just use that, like take screenshots from that to produce your lab. The point of these labs isn't necessarily to get any specific data. What we would normally do with these labs is we would collect data for a material that we were going to later build a physical truss out of. Since we're not doing that part, it's all digital, then the labs become now the point being seeing how you can simulate the same types of things that the real world does. So the first lab was simulating a tensile test, putting a tensile load on a material. This one, lab 2, is going to simulate a 3-point bend test, whereas if we were in person, you would actually go do a 3-point bend test. So I already have SolidWorks up here. Let's get it kind of centered there. So this is what we're going after. Well, that's the top view. We want to create this. So this is going to be a simulation of a 3-point bend test. There are 3-point bend tests and 4-point bend tests, and there's slightly different ones. The 4-point bend test. Let's look at some pictures here, so you can make sure that we know what we're talking about. So here you go. This little picture right here is kind of a schematic view of a 3-point bend test. Here's a actual view, or maybe that's a render. That must be a render. Here's an actual one. So you have 3 points of contact, one in the center, and then 2 supports. Usually the supports are something like in this picture where they're just round. They're not rollers necessarily. They don't literally roll, but they're rounded and they act kind of like rollers. The 4-point bend test is almost the same thing, except it spreads out the center load into 2 locations. So it kind of, if you're worried about your material locally failing under that center load, then you can do a 4-point bend test and you have 2 center loads, and it kind of helps with the localized failure of a really soft material. So same idea, here they are side by side. Same idea, 3-point and 4-point. You're bending like a beam, you're causing it to flex, and then you can record the data all along the way. We're going to simulate this. All right, so back over here, this is what we'll end up with. So why don't we do a new one? Oh, I don't know what I just did. I think I undid something. So new part. Normally these, we would need to go into ASTM and find, what's the required length to width to thickness ratio for a proper test specimen. We're just going to make one that works for our purposes. And first we need to actually go in and build the part. So I'm just going to build it from the top plane. and it's just going to be a rectangle. These are not fancy dog bone shapes like the tensile test. It's just a little rectangle. I'm pretty sure I am in IPS, inch pound second unit system here, so if I am, then this is like 1 inch. This is usually somewhere around 8 inches depending on your machine, and then the thickness is some ratio of these numbers. I'm going to say it's 1/8 of an inch thick. So once it's finished, there we go. So I'm just typing in the dimensions of this thing over in the thickness parameter. Okay. We need a material here, so let's pick a material. And I'm going to pick one that's a linear elastic. I think there's a alloy steel here. Yeah. I want the IPS units, linear elastic isotropic. That sounds good. So this is just some alloy steel. 30 million psi for the modulus of elasticity, and tensile strength at, oh, this is actually a pretty strong steel, 105 ksi for tensile strength. Yield strength at 90 ksi. So it's pretty strong material. We'll use that. Normally you would use the material you were interested in. I just picked one. All right. Now, in order to set up the fixturing, so this is the piece, this is a sample. What we need to do is I am going to apply some geometry that's not really part of the sample. It's just edges and lines that I'll be able to select so that I can fix them or apply a force to them or whatever. So I'm going to do that by adding some planes first. So reference geometry, oh, hold up, we're off the screen a little bit. There we go. Reference geometry at the very top center of your screen. And I'm going to add a plane, and it's going to be in relation to that plane, if I can get it to select it. There it goes. And I'm going to put it in the direct center, so that would be 4 inches right there in the middle, since I made it 8 inches long. I'm having issues with it wanting to select things. Might be SolidWorks is very memory heavy, and so it could be that streaming and SolidWorks at the same time is not the best idea, but we'll carry on if we can. I'm going to make 2 more of these planes. Same reference. Actually, I think it used this plane I just used as the reference. I want this one to be 3.5 inches. So it's kind of a 1/2 inch in. That's not super important, but you would want, this is representing where the supports are going to be. That first plane is going to represent where the load is going to be. We'll do one more, and this one will be 7 inches from where my current reference is, so it's on the other end. You could, it doesn't matter where you reference from as long as you know how far the offset is between it. Alright, so now I have these 3 planes. I'm going to create curves right next to reference geometry, curves. I'm going to split lines. And I'm going to pick the 3 planes that I just, if I can get it to highlight it, come on. Oh wait, I need to be in there. Alright, there, there. And I'm going to split this top surface and the bottom surface. It doesn't actually change anything as far as the volume goes. It's just adding lines on the top that I'll be able to select later. There's a variety of reasons you might want to split something. In our case, the reason is that we want to be able to select these lines later on without them actually being physical features on the part. Like, I don't want to go build in little bumps or anything to select. Here I'm just hiding the plane so I can see the lines. Those are the split lines. So now, normally we would save this part. I'm not too interested in that. This is all we need for our part. And we go to our simulation. So I am going to, this one could work in either one. Looks like I've got the premium loaded up already, so that's what we'll use. New study. And we're going to do a static study. That's why I think the other base version of their simulation would work fine. We could name it, we don't need any of that. And we've already applied a material, so you can see here that there's a material out beside the part. Part 2 is the name of the part. So we don't need to do that. Fixtures, I'm going to model this as if it has a pin and a roller. The real 4-point and 3-point bend test kind of just sit on things that were more like rollers. But if I under constrain a simulation in a finite element package, bad things or weird things can happen. So I'm going to model, say, oh, let's get it turned around there. This line as a fixed support, so more like a pin. So fixture, there is actually a fixed hinge, but I'm just going to do fixed geometry, and I'm going to fix that line. So that's why I added that split line. The one on top here, I actually don't need. It's just a relic of having created that bottom split line with a plane and selecting this top part to create this top where the load's going to be. So I don't actually need that line, but it does exist. All right. Creating the roller over here is a little bit more complicated. Not that much more, but it is. Looks like, oh, there's roller. I'll just put that on there. The problem with this roller slider is that you can only apply it to surfaces, not lines. So instead, I'm going to do advanced fixtures. And this is basically the same thing as the fixed, except it allows me to select specific directions and have them either constrained with no translation, or to not do anything with them, or to give them a specific displacement. So I don't think this works exactly like a roller would, like where it lets the part slide past it, but I'm not 100% sure. This is how we're going to do it. So first I need to select what do I want to be the line, so that split line. I need a reference for it, so I'm going to pick that plane. And now in reference to that plane, wow, I can't get it to tumble the way I want it to. All right, in reference to that pink plane, I'm going to have, let's go ahead and put it in inches since everything else is inches. I'm going to select one or more of these directions in reference to the pink plane, and I am going to assign it a certain amount of translation. So that's the one I want. I want it to not translate up and down. You can see the green arrows are pointing up and down on the blue line. I want it to translate 0 inches in that direction, so I'm going to leave that just like that. So I clicked this button, and I don't know if you can see that, kind of over in that area. I'm going to leave these alone, which I'm not sure 100% how it deals with the ones that I don't select. It should just ignore them and technically allow this to move left and right, but I don't think it does that. But we'll still carry on. Okay. Now we just need a load in the middle. So external loads, right click, I'm going to apply a force. I'm going to apply a force to that line. I want the line in a certain, right now you see the force is kind of pushing that direction. I need it to push down. So I'm going to do selected direction. The pink plane reference I'll use is just that one. And then there's the arrows, but I want them pointing down. So reverse direction. Let's put it in US or IPS units. And let's make it, I don't know, 50 pounds. This is a 1/8 inch, 1 inch wide piece of steel that's pretty strong steel. Maybe 100 pounds. There we go. I'm just trying to figure out what will cause it to deform. Now my simulation can exaggerate the deformation, so it looks like it's bent way up when it doesn't actually do anything. We could do a lot more fine tuning and all that, but I'm just going to right click mesh. Where's it at? Mesh and run. Okay. So this should not take very long, just being, there it is, already done before I finish saying it's not going to take long. So now what you do, probably what we should have done first, is look at our mesh. So here, if I right click on our mesh and show it, we can actually see what the mesh looks like. Most of these elements look reasonable. What you're looking for here are any really distorted elements. These are actually kind of distorted. Like right here, these in this row are a little bit longer than they are wide. So that's not great. Is it a problem for our simulation here? Probably not. Also, I have a different type of element over here compared to everywhere else. That's a little weird. Except for this piece, this surface is not even doing anything really. It's the overhang. So that's okay. Let's see if I can find details here. So these are my mesh details. It looks like I have elements that are 1/10 of an inch in size. A side is about 1/10 of an inch. I have 9,258 total elements here. That maximum aspect ratio is kind of the length to width shape of these elements. So that will tell me, 3, it's not horrible, but it's not great either. I'd like them to be more square, although they're triangles, but you know what I mean. So it does say that, well, most all, 100% is what it says, but clearly there are some that are not, have aspect ratios less than 3, which is good. But there is some number that has slightly over 3. None fall into what we would call distorted, which we don't like at all. So that's kind of the overview of what this is telling us. Our stress plot here is also showing us our displacement. Now, our deformation scale up here is 5.5. That means that this shape is 5 times greater than what is predicted to really happen. Usually you also go in here and animate to kind of get an, going too fast, slow it down. So to kind of get an idea of, is that what you expected to happen? And yeah, more or less that's what I expected to happen, although it's hard to tell if there's any actual sliding happening on my roller, but maybe there is. It does kind of look like it slides past it, maybe. So normally you do go and check your video animation of the simulation to see if it looks reasonable. Other things we could do, well, we could go in and scale. Let's see, I think is it chart options? Or it might be edit definition. Well, we could put it in KSI. Von Mises stress just means combined stress for what our purposes are. We haven't done that in class. We've only done principal type stresses. We could do true scale so that we see what it really thinks it's going to look like. So there's what it really thinks. Let's see, we can also, let's see, I think in settings we can make it have like a transparent superimposed model on the deformed shape. So we can do that. And you can kind of see that grayish box is the original shape, and then that's what it's thinking it will do as in the real world as far as deforming or flexing downwards. So it's a super simple simulation to do, not very complicated at all. A couple of little details, getting the roller over there versus another fixed support. The thing with the fixed support, if you fix both of these lines, so if you fix this line and that line completely, then when you go to push it down, with the force in the middle, then, and it's held tight in both ends, and you want to cause it to flex downward, that's going to induce new stresses, new tensile stresses in the part, which wouldn't be there if it's really sitting on rollers. So a normal 3-point or 4-point bend test doesn't fix the part down, the sample down. It lets it slide back and forth if it needs to. With this amount of downward deflection, it probably isn't even trying to slide very much. All right, I guess we could let's see how different it is, because I'm actually not 100% sure that it's really treating this line as a roller. So let's change that one to a fixed support and see if our von Mises stress actually does change. So right now we're at 6.7 times 10 to the first. Those are KSI. So we're at 67 KSI as our max stress. So let's go to our fixtures here, and let's Let's delete that one. This is the roller. Yes. And we will add another fixed geometry on that line, just like we did on the first line. Rerun the simulation. It's giving me a little error that these results no longer apply to the current setup. We're going to create a new one. And let's see what it says. So yeah, we get a very different stress, but it's lower, right? 49. The other one was 67. So that's a little weird. It's actually a lot weird. I'll have to think about why that dropped by 17 KSI. A little bit strange to me. I would have thought it would. Oh, you know what? It could have been a compressive stress was maximum, and I've kind of negated the compressive stress. Oh, so this is. I think this is what's happening. I'm not 100% sure. I think what is happening here, where we had a 67 KSI when we had it fixed as a roller, versus a 50 KSI when we have it fixed. I think this is not a real thing. I think this is an effect you get when we applied this load. We applied it to a line, right? And so probably if we had more detail, like more elements around this line, what we would see is that we're getting really high stresses right at that line, and they're compressive stresses. Literally the bar or our load pushing down on our member here, and the 67 number we had was probably a really high compressive stress right on this line. But now that I've locked it down here, it's kind of adding tensile stresses everywhere, right? Because it wants to get shorter, but it's not allowed to, so it's stretching everything out. And I bet those tensile stresses are removing, or counteracting some of that high compressive stress that's right under the load right here. I would assume that's probably, in fact, look, there's red on top and bottom is relatively low, and that's not like a negative and positive thing, it's just a magnitude thing. And so it is that the compressive stresses on top of the beam are being a little bit counteracted by locking the beam down and putting everything in tension. So you have to be careful. So I think our way of creating the roller was actually working. I think it was working correctly. But we were still getting some really high compressive stresses on top of the beam here. So if we went, I don't know if I can just undo. Oh wow, that gives me all kinds of errors. How many undos do I have? All of these are just viewing it. Still show. Oh, I think I ran out of undos. So let's see if I delete this guy and then replace it with our advanced fixture, and we're gonna. Oh, wow! Why are we not showing our? That's a little weird. I guess because I have it. That's going to be hard to do, isn't it? Probably should have undid a bunch of actions. Let's just see if we can do it. Yeah, I'm not going to be able to select the lines right now because of the view that I'm in, and I don't exactly know how to change the view. Yeah. Well, it's fine. So I was just going to go back to the way we had it with the roller and verify that the compressive stresses were higher on top than on bottom, than the tensile stresses on bottom, when they should be equal. All right. Anyway, you don't have to do all of that part. Just do your rectangular beam. Doesn't really matter the dimensions, but there are some dimensions that are more approved, like ASTM approved dimensions for a 3-point bend test. I'm not worried about you getting those dimensions exactly. Do their split lines so that you can apply your load in the middle and your reactions, however you want to do the reactions. I would suggest trying to do the fixed support on one end, and then something like the roller on the other end. If you can't get the roller thing to work out right, just go in and do them both fixed, and you'll at least get it to simulate the something like the 3-point bend test. All right, that's all of that. I saw a couple, one question about SolidWorks, but that ended up working. Is there a quiz where we pick the time? No, on these, I needed those quizzes before because we were doing in person with some people, and I needed to know how many to make. It doesn't matter. The only thing is you can't pick both times. So you have to pick one. Once you start one of them, that's the one you're doing. So you can't start the noon one and then decide you don't want to and come back later and do the 7 o'clock one. So you got to do the whole one that you pick. But you don't have to tell me ahead of time which one you're picking. All right, so there was a question about a machine. Let's go over. Let's close SolidWorks before everything crashes. We don't need that. Let's look at. Let's see if there's any in the optionals that would be good as samples for machine. Machines actually might be an optional one, but I don't know. These are all frames. Frame. And then we jump right into beams. Okay, so those aren't going to be very helpful for us. These are all beams. Let's see if there were any in optional one. Wherever it went, there it is. They'd be at the end. That's just a rigid body, trusses. No, no, no. All right, so they're not in there. Maybe anything in here? That one is sort of machine frame-ish. That's just a complicated beam. So nothing there. Maybe in the regular homework set. Oh, I know what. Let's look on the sample test. See if there's anything in there that's frame-ish. I mean machine-ish. Centroid or moment of inertia stuff. That technically is a machine that's super simple. Let's work that one just to do one, but let's see if we can find something better than this one. Now, remember, these are retired exams, so they could have mistakes in them. I don't know. But let's see how this one works out. Oh, I'm going to have to rearrange my setup here so I can write on my screen. I had it working for SolidWorks and not for this. Okay, there. All right. So this is about as simple of a machine as we can get, but it is an example. The difference in framed machines. So no difference in the way that we solve them, except that for a machine, typically we have to start by taking it apart, whereas a frame, usually, but not all the time, but usually the first step is to find the external reactions. So that's the difference. The technical difference of what makes one or the other is a machine just has parts that move relative to the other parts. So here, these are some kind of plier looking things. And so the two halves of the plier move relative to each other. Whereas frames, everything is supposed to stay in the same orientation. Kind of like a truss, except some of the members have forces directly on them, and they're not two-force members. So the difference is machines have moving parts, frames are not supposed to have moving parts. All right, so this one is super simple. This one is a set of pliers, which they're supposed to have parts that move relative to one another, which put them in the machine category. When they're in the machine category, you think, oh, usually what I have to do here is just take it apart first and then solve for some of the forces. So let's see what it even wants me to find. It wants me to find, whoa, all right, we gotta make sure that's not happening. We want to find the value for P. So P is applied to either one of these, either the light gray or the dark gray part of the plier. So I'll just pick the light gray one, and why don't we do it this way? I'll just kind of trace over it. And okay, something like that. And we'll, oh, also we have that in there, don't we? Okay, and we've got a point load that we don't know the value of. We just know it's named P. And then this pin, it doesn't have a name, but we'll call it pin A. It's going to have two forces because it's a pin, two reaction forces. I don't know much about them, but I'm going to put well, actually, hold up. For this one, I'm going to put AX going this way. I'm only doing that because that gives me more room to draw it. And then the bolt is making contact, this little dark gray circle is making contact with the jaw, the lower part of the jaw. And so there's some kind of force there. And I will call that, well, it says, the bolt shown is to be gripped with a force of 33 pounds. Okay. Then the force P required at the handles of the pliers is closest to. And I've got a couple of dimensions here. I've got the distance from the load to the pin at A is labeled as letter A. And for me, so AX is just going to be 0. And I'm not interested in AY. The problem's asking me about P. So if I do summation of moments about point A, which I'm calling the pin at is A. So that's A. I would get 33 pounds times 1.4 inches minus P times 5.3 inches equals 0. Therefore, P equals, I don't know, let's see. 33 times 1.4 divided by 5.3 is 8.72 pounds. And fortunately, that does match up with E there. So that would be our answer. That's about as simple as we can do on a machine. Two parts, two moving parts, and it's basically just a lever. Let's see if we can find something more interesting than that. That's a frame, beam, centroid. Even though this is on the Exam 2, Exam 2 used to have centroids on it. Centroids are not part of Exam 2 unless you need, or think about it as in the context of you need to find the neutral axis of a cross section. But I don't think there's anywhere you have to calculate the centroid. It's just given to you. And there's definitely not any of these integral versions. That's kind of, it looks like it could move, but it's really not meant to. These are more beam. Alright, so we're not having a lot of great luck finding a machine problem to work on. I wonder what happens if I do, these are more interesting. Do we have enough detail in that one? It's kind of small. Oh, these would be good. This is a problem from, I don't know what textbook, but that one's more interesting. It's got some drawing on it that we'll have to ignore, but we can do our own version of this one. Let's see if we can find this picture. Hey, there it is, right there. All right, let's do this problem. So I don't know what book this comes from, but it is clearly some kind of textbook. And we have this bolt cutter, so similar to what we had before, but there's more pieces now. A worker is applying two 75-pound forces to the handle. So basically they're trying to cut some kind of bolt or whatever, and they're pushing on both handles each one was 75 pounds. So this one's working backwards from what we just did. The one we just did, we knew the force applied to the bolt, and we figured out how much force to apply to the handles. This one, we know how much force we're applying to the handles, and we want to figure out what's getting done to the bolt. Okay? The only problem is we don't know the right answer. So hopefully we do it correctly. We decide this is a machine because it is intended for this to have moving parts. Oh, there is one. I couldn't find one in the web work. Oh, maybe the actual homework. Okay, I didn't think about that. I know because I don't remember. What homework is that? 12? No, probably not in there, huh? That's more beamy, so it's earlier than that. We can, if I can find the web work version of something like this, that would be great. Trusses, so it's must be after that. So where are we at? 9 or 10 now? Here we go. That's actually kind of a machine frame-ish thing. So maybe in here, frame, another frame. That's that one we actually worked on that one some. All right, so maybe in 10. That's a, or I guess 11 is also possible. Let's see. Where's 10? That one's kind of machine-ish and a frame. So we do have some in here. Hey, there's the there it is. That is almost exactly the same thing. Let's do this one since we have this one set up as a web work. And it does look like it's going to work exactly like the one. Yeah, no, it's exactly the same problem, just smaller picture. Yeah, that's exactly the same. All right. All right, so same idea. We've got a bolt cutter, except here, no, we do know the force applied at the handles. Different force. This time it's 66 pounds. And this is not technically a bolt cutter. This is a crimper. So it's crimping a ferrule, like a metal sleeve around something like a really big cable, like a battery cable or something. So instead of cutting it, it's crimping it, squeezing it down. All right. We are given the assumption here that that the crimping part, the center right over here, the forces are completely vertical. They're not coming at any kind of weird angles, or we don't have to do any projected area type of thing. It's just straight down force on it. That's probably not quite true, but that's what we are told to assume. All right. So again here, the external forces we actually know. Like they told us what F is. And so there's no reason to try and solve for the external forces, so we start by taking this thing apart. Now there are 1, 2, 3, 4, there are 5 pieces to it, plus the crimping that I colored in green. But 2 pairs of the pieces are really just mirror images of one another. So we're gonna assume anyway that they're gonna have symmetric forces. So we really only have 3 pieces to work with. And the other thing with this is part AB is a 2-force member. So part AB is just a vertical piece. Doesn't matter what orientation it is, but it is vertical in our picture. It has 2 pins, A and B. There are no forces acting on part AB other than at the pin at A or B. So AB is a 2-force member. So that could come in handy. So we really only have 2 pieces to work with plus this 2-force member. All right, so usually it's best to start with the one where you know something. So we do know the handles have a force F. So why don't we draw one of the handles first? So I'm going to do the same thing again where I kind of trace it. Get off of there. And then we'll get some of the other pieces, which I don't need, but that's fine. make it a little bit bigger so that we can work on it. Get rid of that. It had a force kind of close to the end. So we'll put that right here. We know this force in our problem statement, 66 pounds. We have 2 pins. They are labeled D. Okay, so about those pins though, I don't know a whole lot. So I've just got DX. Is that D or is that C? That one's D. I've got DX and I've got DY. And just to save some room here, I'm going to put CY going this way. I don't actually know anything about which way they're going. So the problem here is I have 4 unknowns. What dimensions do I have? I really only have the horizontal. I have a couple of vertical dimensions, H1 and H2, but I don't see any way that I'm going to be able to do a moment or an X or a Y equation and solve for anything. So that's a little concerning, but we're just going to carry on and we're going to draw the next piece and see if that helps us at all. So this piece, let's get rid of this. All right, I'll trace this little guy. And let's move him down here with our other pieces. Enlarge it so it's kind of the same, somewhere near the same scale. I don't know how, oh, whoop, whoop. There, whoa, why are we? Look like they look like they're on the same line. I'm not 100% sure they are, but it kind of looks like they could be. But since it doesn't tell me and I'm not 100% sure, I'm going to draw them not on the same line, and because I don't know. It might make things simpler if I knew they were on the same line though. All right, so I've already drawn arrows for D, so I've got to draw the corresponding reactions here. DX, and I made DY on this piece. It needs to go down. I have not drawn anything for A, but I do remember that AB is my 2-force member, so I don't have to draw an AX. I am going to assume that AB is vertical, and so the force, the force in that 2-force member is also vertical. So I am going to assume that. Let's just make it go this way. And I know this. This is the thing I'm actually trying to solve for. It's called, well, it's the clamping force, I guess. So we'll just call it F sub C. No, because we have a point C. Let's just call it clamp. Okay. Now I see what we can do. So based on this diagram, since I knew that member AB was a 2-force member and I did not draw AX, right? So since I didn't draw AX because I'm assuming it's a 2-force member, because it is a 2-force member, and I'm assuming that the force in the 2-force member is vertical because of the way it looks in the picture, then that means that this part of my bolt cutter, or crimper in this case, does not have any forces in the X direction, which means DX has to be 0. Now if FAB was at some angle, or if this clamping force was at some angle, then yeah, that's a whole different thing that we probably can't solve with our knowledge right now. But once I make these assumptions, DX is 0 here, which means DX is 0 on this piece, which also on this piece means that, well, if DX is 0, then CX has to be 0. So now suddenly I got a set of problem pieces that are way easier to deal with. And it really just becomes 2 problems like the first one we did. So I end up with this dimension and this dimension, and I believe they give me those, 9.6 inches and, well, 9.6 inches here, and I think this was 0.86 inches here. Yeah. And all I have to do is summation of moments about C equals 0, and I get dy times the 0.86 inches minus 66 pounds, the external force applied to the handle, times 9.6 inches. And I find a value for dy. 66 times 9.6 divided by 0.86 is, now we're getting the multiplying effect of our lever arm, 736.7 pounds. I can take that dy to the other piece, and I can do summation of moments about, that's A, this is point A, and I have the clamping force times, let's see. These distances are 1.27 inches. And 4.9 inches. Okay, so the clamp times 1.27 inches minus, oh wait, no, that's actually plus. Yeah. Plus dy times 4.9 inches. Did I get dy? Oh, because this dy is negative. Because that should have been a plus sign. There we go. I was wondering why that was the clamping force was flipped around the wrong way. So this dy here that we originally solved for should be a negative number because I left out I've made that a negative sign. All right, so dy is negative. So let's see. We found a value for dy that we can plug into this equation. So negative 736.7 times 4.9 divided by 1.27 gives us a clamping force equal to 2,842.56 pounds. So I apply 66 pounds of force to the handle, and I get nearly 3,000 pounds of force at the clamping jaw. Hopefully that gives our web work numbers. So now the way this is set up is trying to deal with plus and minus signs. So what it's saying is the body exerts a whatever force. So the crimp ring, so that's the thing being crimped, exerts a force on AD, which is the top jaw part. The horizontal is 0 because it told us that it didn't have any component. It's purely vertical right here. And the vertical magnitude was the 2800 number. Do we put units? Yes, so these are pounds. And I guess we need to put 0 pounds also for horizontal. And we got both of those right. So we're actually dead on. Actually, that's exactly the number I got. 308. Yeah, I have all of those decimals. So that's kind of how that's working. On an exam situation, first of all, there's not going to be this many blanks for one problem, unless it's a more than 6-point problem, and each blank counts for you know, a piece of the points, but there wouldn't be this many anyway. And I'm not so concerned of the force that this body exerts on that body. I just want the magnitudes of things. And so then we would have to figure out AB, so that's the little vertical two-force member, exerts on AD. We actually solved that one, right? Oh no, we didn't do that. That's FAB. So to get FAB, we would need to take this free body diagram here and do the summation of forces in the y direction. So then once we've, you know, depending on what you're trying to solve for, you start working on that free body diagram and doing your x equation, your y equation, and a moment equation. So that would be continuing all of that stuff, doing the forces in x or y for each of these two free body diagrams would be the rest of solving this problem. The key to this one, though, is this piece, recognizing that that's a two-force member. If you don't recognize that's a two-force member, then when you go to draw this free body diagram, you have to put AX and AY, and you never get the realization that AX is 0, therefore DX is 0, and if DX is 0, then CX is 0, so you don't ever get that chain reaction of eliminating unknowns, and you can't solve the problem with the methods that we're using. Yes, so the question is, so for a frame or any frame or machine question, I am probably more than likely going to be asking for, if I say the force or the reaction at pin C, for instance, what that would mean is you find CX and CY and do the square root of the summation of the squares. So just to be sure about that, C equals the square root of CX squared plus CY squared. And C is the thing I would be interested in on the exam. And I wouldn't really care about if you think it's positive or negative, because it depends on, you're talking about the C there or the C that's on the other part of the, you know, we didn't draw that one, but the C that's on that piece, because one of them is one direction and the other is the opposite direction. So I'm really interested in the magnitude. Could we do a flexural stress? Yeah. So flexural stress, is there a particular flexural stress problem? There's not in this homework set. Maybe, does this have any good flexural stress problems? Moment of inertia. These are more about, oh, here we go. I don't think we've worked this one, so maybe we can do this one. Well, one where we do need to find inertia. This one we do have to find the moment of inertia, although it's not terribly complicated, but we do have to find it on this one. So this is 15.3. Okay. So, first of all, let's see if we have symmetry. I do not have symmetry. It looks kind of like symmetric. It could be symmetric, F1 and F2, but the F1 and F2 are, first of all, they're not the same value. They're different forces. And they're not the same distance from their support. So it's not a symmetric thing. Why I would want to know if it was symmetric about, you know, a axis here is, if it was, then I know that the maximum flexural stress is in the center of the beam. But it's not, so we can't take that little shortcut. This one's actually asking us for several things, though. So first of all, it tells us that the section is a tube, a steel pipe. Now, you got to be careful with steel pipes, because this one is a steel pipe with a particular outside and inside diameter. So that's fine. But let me check our, here we are. trying to load. There we go. Probably in the exam reference. I don't know which one. All right, here we go. I need to rotate it around to where it's right side up though. So this little table, I know you can't read that at all unless you're on a really big monitor. It's even hard on a big monitor to read. But this table is table A13, and it's called Properties of Standard Steel Pipe. And so what these are is if you're given a nominal pipe. So, you know, it's a 1-inch nominal standard weight pipe or a 1-inch extra strong standard steel pipe, then what that is telling you is the 1-inch part is just its name. And you have to go into a chart like this to see what the actual outside diameter and inside diameters are. So this problem that we're working on, it actually gives us the outside and inside diameter, so we don't have to go do that. But if you had a problem and it was a steel pipe and it was a nominal whatever inch, and then there's 3 categories. There's standard, extra strength, or extra strong, and I don't remember the other one. Double extra strong. So yeah, super secret extra strong. This one we just use these numbers though. So let's draw our cross section. Let's actually not draw it in blue though. Okay. I'm not going to get it perfectly lined up, Emma. So it'll be fine. So I'm just enlarging this section that they have over here. So I've got 2 circles. So we need to go get our moment of inertia for circles because I don't remember it. First of all, we don't, in this case, have to find the neutral axis because we just know that it's the center. The centroid's right in the center of this thing. Looks like I drew it a little bit low, but looks like it's going to be hard to move. Yeah, it'll be fine. Now, on exam 2, I do not think most of the problems that you have to do where you're calculating the moment of inertia, we're just going to give you the neutral axis location. So you don't have to first go find the centroid and then do the neutral axis. Or there's something like this where the centroid's just in the center. Or it's a beam that in the chart it tells you where the neutral axis is. Alright, so let's find our equation or reference. Does it happen to be in this one we're looking at? No. We want moments of inertia. And we want moments of inertia for a circle right here. So pi r to the 4th over 4. Remember, we have 2 of these. The x prime axis is at the tangent line of the circle. I don't want that. I want the moment of inertia about the centroid, which is pi r to the 4th over 4. Okay, so that's part of it. Oh wait, well, all right, we can go this way. But we have to subtract out the hollow part in the middle. So OD and ID, that's outside diameter and inside diameter. And then I did OD over 2 and ID over 2 because the equation is pi r radius to the 4th over 4. So our numbers would be pi, our outer diameter is 3.9 inches. And our inner diameter is 2.8 inches. And we can calculate our moment of inertia that way. So this one is not a terribly difficult moment of inertia to calculate. It's pretty straightforward. So I think I get 11.356 for the first part. And 3.0172 for the second part. So eight 0.3388 inches to the fourth is our total moment of inertia for the tube, the hollow tube. We can't check that one on this web work problem, so hopefully we're right, but we can't check. Okay. Now it's asking us for flexural stress at point A. So there's a multiple A's here, but this is point A, which if you look here, it says point A is at the top of the beam right there. On section AA, section is this line over here. And if that section is 4.5 feet from the right support. So if, oops, wrong one. This distance is 4.5 feet. Oh, no, not that distance. Sorry. If this distance is 4.5 feet. Okay. All right. So when you're given a specific section, that's usually an indication that what you need to do there is not draw the whole shear and bending diagram, but go and cut that beam open at that section and find the internal bending moment directly. Now, in order to do that, I either need to know the reaction at C or the reaction at D. Why don't we work with the right-hand side since it's a little bit shorter, and we'll do the reaction at D. So to get the reaction at D, I can take the whole beam, summation of moments about C, the pin, and that will be F1, which for me is 900 pounds, times distance A, 3.5 feet, plus F2, which for me is 2070 pounds, and it is a distance of A plus B, 18.7 feet, minus dy, it's just a roller, times A plus B plus C, 20.4 feet. Okay, so we should be able to solve for dy. $2,051.9 pounds. That seems reasonable anyway. Now we're going to cut the beam at section AA. I'm going to draw the right hand side, so that's going to look something like this. And I wish I could make dotted lines without just having to erase, but I don't know another way to do it. So that's kind of showing that it's a hollow tube. We've got our support reaction at D right here, and it's 2051.9 pounds apparently. We've got F2, which is 2070 pounds, and it's maybe right here. I've got my internal shear, which I don't really need, and my internal bending moment, which is what I'm trying to solve for. The moment at C. Oh, no, not at C, at section AA. There we go. We have a couple of distances. We've got this one. They told us that the section AA is 4.5 feet from the right end, or the right support. And then we also have this dimension from our problem statement being 1.7 feet. Okay, so if I want to find the moment at section AA, do the summation of moments about the cut, and that will give me the moments. Just enter the equation. You don't have to multiply times the distance. This one is drawn clockwise because of our agreed upon scheme for internal bending moment and shear forces, and I say clockwise is positive, so it's just the moment on section AA plus 2070 pounds with a moment arm of 4.5 minus 1.7 is 2.8 feet. Minus, because the counterclockwise about the cut, I guess I should make sure, this is our cut end, the left end. 51.9 pounds times 4.5 feet. So we should be able to solve for the moment on section AA. This is the internal bending moment on that section. And it should equal 2070 times 2.8 minus 2051.9 times 4.5. So it should be, that term is negative, but I move it to the other side, it becomes positive. 37.55, those units are foot-pounds. The internal bending moment being positive means that the beam is bending with tension on the bottom. Moment. Okay. Remember, tension on bottom of the beam, positive internal bending moments, tension on the bottom, compression on the top. All right. Now what we're actually trying to solve for is part A. The flexural stress at point A, so that's the top of our little cross section here, where that distance is half of our outer diameter. It's our outer radius. So 3.9 divided by 2, 1.95 inches. That's going to be the value for y in our flexural stress equation. Sigma, they called this one sigma A. Yeah, sigma A, capital A. So it's the stress not on section AA, but at point A. Sigma A equals negative m times y over I. So negative m, 3437.55 foot-pounds. I want to convert those to inch-pounds. Times y is a positive distance of 1.95 inches. It's going from the neutral axis to the top of the beam. And then we've got I, that was the first thing we calculated. I got 8.3388. And if we have not rounded too much and not made any mistakes, then this will be our answer for part A. Let's see. 37.55 times 12 times 1.95 divided by 8.3388 gives us 9,646.3 psi. Let's see the question. When doing parallel axis theorem for y squared, the y is the distance from the centroid to the desired axis, whether it be neutral. Oh, yes, yes. So, yes, not this y. Not this y. This one is the distance from the neutral axis to the point of interest on that cross section. But when you're doing parallel axis theorem, the y is the distance from the centroid of the part you want to move around, or its effect to move around, and the place you want to move it to. So normally, that is the distance from the centroid of the part to the neutral axis of the entire shape. But it could be that a problem is just saying, calculate the moment of inertia about this random axis I gave you. In that case, y is the distance from the centroid of the part you're working on to that random axis. Let's see if we got this right. Here we are. So it is, oh, wait, we're not quite right. I left off my negative sign. So this is actually a negative because it's compression on top of the beam. So negative 9646.312. That would be PSI if we put those in. Let's see. If we're, no, it doesn't like PSI. We have to write numbers, but it doesn't like PSI. Maybe we have to spell it out. Pound per inch squared. Doesn't like that. Is it pound force? All right. Do I not put units? Maybe this one doesn't want units. Oh, no, yeah, they're already right there. They're already written out, PSI. That's why it doesn't want any units. All right, we were correct. So from here, it gets a little bit easier, at least for part B. So part B is the flexural stress at point B on section AA. So same section means the same internal bending moment. And point B is just a new point. So point B is just down here. So what happens is I calculate this distance, which is the internal radius, so ID 2.8 divided by 2 is 1.4, and it's negative 1.4 inches because I'm measuring from the neutral axis downward. So the only thing that changes in my equation here, sigma B is negative m times y over I. Negative, same internal bending moment. Still need to convert over to inch pounds. But the distance y is different, and it's negative. And then the same moment of inertia for the cross section because it's the same cross section. So this one will come out positive because tension, the positive stress, is on the bottom of the beam, and we're measuring towards the bottom, not the very bottom, but towards the bottom. And looks like it's positive 6925.56 psi. And that's in the range of a reasonable number. It's positive, so it is a tensile stress, and it's a little bit less than the compressive stress we just calculated because the compressive stress was all the way on the outer surface, all the way on the outer surface of the beam, and the one that we just calculated at B is not all the way at the bottom. It's kind of, whoops, I didn't know that would erase. It's kind of near the bottom, but not quite as far away. So I think this is the right number, 692556. Yeah, the same number. The last piece here, the last part is different. The last part says the maximum flexural stress anywhere in the beam. So what that is telling you is that you need to find the maximum bending moment anywhere in the beam, which means you need to draw the shear and bending diagram for this one. And you'll end up with some bending diagram that shows you where the maximum internal bending moment is located. Then you take that one, and as far as, do you use point A or B, you would use point A, either at the top or all the way at the bottom of the beam, because you want the maximum worst case number that this equation would generate. And that means that all of these numerators need to be as big as possible, and the denominator needs to be as small as possible. You can't change the denominator because it's just the cross-sectional shape. So you find the largest value for M and the largest value for Y. And that'll give you the maximum flexural stress. But in order to do that one, since we can't just tell from this diagram that the maximum internal bending moment is in the very center of the beam, we have to go draw the diagram to figure it out. All right. Any other last minute things before we close it down? I think I've answered all the stuff in the chat so far. Oh, I know there's a 10 or 20-second delay between me and the chat though, so I'll give it a little time. All right, so far I don't see any new chat things, but just so you know, this exam 2 works just like exam 1. I believe the drop day is the day after the number 6 on the practice exam. We can look at that. I believe the drop day is the day after the exam, so it'll work the same way where you'll get a grade immediately. Like Canvas will grade it, and it does a lot of the problems correctly, but it doesn't do everything correctly. So just know that the grade that you get immediately, whenever I get to do the whole set of them, like review everything, you'll get some more points, just like you did on exam 1. I don't know how many more, because it depends on how well Canvas does grading it, plus what particular questions you answered. Where's my... There it is. Let's see if number 6 is worth doing. Oh yeah, okay. We haven't done too many or many like this one, so this is a good one to do. So this one is dealing with distributed loads. It has an evenly distributed load, the W2, and an unevenly distributed, the W1. So the point of this one is that if you were trying to find the reactions like at A or D, then you would need to know how to lump these loads, these distributed loads, together into point loads so that you could actually write your moment equation. Now this particular one is saying I want to lump all of them together instead of 2 individual lump loads. Like you could do this, right? You could put one here and one here and find the reactions, but this particular problem is saying if I just put one, like one lumped load for the whole distributed setup here, where do I put that? So somewhere like, I don't know, maybe here. Where does that go? So all you do is you find the centroid. You treat these red, triangle and square like they're areas. So instead of thinking of them as loads, think of it as just a shape like, this and this and this and this. And you find the centroid of this area is what it's really just asking you to do. So let's put our dimensions on here. Now it doesn't matter how far in the y direction, we only want to know the x direction. So for this set of numbers, A is 5.1 feet and B is also 5.1 feet. The heights, so you know, if you were doing a centroid, you need to know the heights, right? So for distributed loads, the heights are the W's here. W2, so the height here is 500 pounds per foot. I'm just going to leave the units off, but it would be 500 pounds per foot. W1 goes from 0 at the pointy end to some height over here, which is labeled W2. Oh, missed. W2, oh no, W1 is 800. Okay. And now we just find the centroid, and it wants us to measure how far from the left support. So the pin is the left support. So it wants us to put basically the y-axis right there. And the x-axis would be along the bottom, I guess. And so how far from the y-axis? So we've got the part. So I guess this is, if one of these shows up on exam 2, this kind of is just calculating a centroid, but in the context of a distributed load that would go on a beam. So maybe these show up on there, I don't know. But we'll go ahead and solve this one. They have in the past been on exam 2. I'd have to look at the outline and see. This would be called distributed load. So if you see anything called distributed load, it could be one of these problems. So the area, I need to calculate. The area for part 1 is just a triangle, 800 times 5.1. The tricky part is to remember divide by 2, so 2040. I think I put inches squared, but I think that's not the actual area, right? Maybe we'll put area in quotation marks because it's really a force, right? Because these are distributed loads representing forces, they're not actual areas. For this one, 500 times 5.1 again. Whoops. So this total, 4950. And then we need the x. This will be in feet. So for part 1, it's a triangle. So maybe you don't or do remember where the centroid of a triangle is, but you do have that reference sheet that would tell you that this distance is 2/3 of the base. Actually, I think it gives you the other distance. It gives you 1/3 of the base measured from the centroid to the right angle part of the triangle. So this is 2/3. So 5.1 times 2 divided by 3 is 3.4. Oh. And then for the square, or not square, rectangle, you just want that distance, which is half of 5.1 plus all of the 5.1 of the triangle part. So 5.1 plus 5.1 divided by 2. 7.65. And then I have AX, A times X. 2040 times 3.4 is 6936. And 2550 times 7.65, 19507.5. I sum those up, and I get 44.3.5, and X sub C, or the location of the distributed load, is 26443.5 divided by 4590. 5.1 5.761 repeating. And those are feet. So it looks like this is another one where E is the actual answer. And what it's telling you is that if I were to replace these two distributed loads with one single load, I'm going to draw it in red this time just because I've already drawn purple ones on there. I would go to 5.7 feet, so somewhere right in here. So what is that? 5.761, and I would put 4,590 pounds at that distance, and that would give me the same effect as far as moment, you know, calculating moments about A or D. That would give me the same effect if I were trying to find reactions. It's not the same effect as like stresses go. You know, the distributed loads act differently than point loads as far as stresses go, but when you were just calculating a reaction, then I can lump them all together. And so that's what this problem is asking. If you see a thing on the outline about distributed loads, it could be a problem like this. Okay. I don't see any other questions yet. What else was I saying about exam? Oh, same rules. You can print out or have open the exam references or your book. If you have the physical book, the exam references are just straight from the book, so you can have that. Or if you have the PDF of the book, that's fine too. So you can have those things. You can have your calculator. Just don't try to do any in MathCAD. You're going to open up Zoom, make it where I can see. I don't need to hear you, but I need to see you in your Zoom. And the exam will open at 12. If you have extended time, it'll automatically, or should automatically, give you that extended time. It will grade right away. I think the next day is the drop day. Remember that on the way the final grades are calculated, of exam 1 and 2, the one you do worse on is a smaller percentage. So you might have to go back and look at, I assume it's in the general tab. I don't actually remember where I put it. Grading. Yeah. So the lower one is only 15%. The higher one, the one you did better on, is 25%. Final exam, exam 3 is 25%. The final exam is a bit comprehensive, so it covers things all the way back to resultants, and some new things that we'll cover between now and the final exam. And everything else is, you know most of the other grades. You should know what you've done in web work. Design project, that's going to be another SolidWorks group. It is a group thing. The 2 lab assignments are just the things we just did, one of them. You just need to write your version of it. You can retake exam 1 or 2. Remember that. It's not the exact same exam. It's just another version of the content. And whichever, well, no, not whichever. If you retake it, the most recent version is what your grade will be. Even if you made lower, although, I mean, the people I can think of that made lower on the retake, they made like a single point lower in 20 years of having that. And most people improve by 7 to 10 points. Okay. How much are the bonus homework? Oh, the bonus homework. So in here, homework, web work 10% thing. If you were to do, let's see, where are they at? If we the essay or the bonus ones, if you were to do all 3 of those, we haven't opened up 3 yet. So if you did all 3 of essay 1, essay 2, and essay 3, then you would get 3 extra points in that category. So you could get up to 13 points out of your 100 points there. So I guess I would say they're each worth 1 point on your final grade. Oh, number 5. Let's see. Do we have time to do another one? And where is it? Oh, I guess I closed it out when I clicked over here. Let's see what number 5 is. Maybe we can talk through it. I don't know if we have time to do it, but we can at least look at it. Oh, and quiz 4 is open, but I moved its due date to be after exam 2, so you don't have to do it before exam 2. You can try it. I think you can try it twice. Oh, so this one's not terribly... I will draw one piece of this one because that's the key to it. But I don't think we have time to solve the whole thing. So this one's got a little bit of a unique part that you have to learn how to interpret. It doesn't... it gives you a hint here. And it's got another part that's a little interesting. So the interesting part here is the diagonal piece. So the diagonal piece is something like this. And it's got this little weird thing going on up there. No, not like that. Like that. So at C, there's nothing special going on. First of all, there's no two force members. You might think that BCE is a two force member because it only has two pin-like things, but it also has a force at E, which is not at a pin, so it's not going to be a two force member. C is just a regular pin. So you go and you put your CX and your CY. If you read the green highlighted part, it basically says that E is a roller, even though there's not a wheel there. It's acting like a roller. So you do this. And then the weird one that it doesn't talk about is that that thing at B. So what that is it's like a slot, but it's not, it's not contained in a slot. So technically the diagonal part could kind of rotate clockwise if it was allowed to, away from pin B. So what you do when it doesn't tell you a particular thing, is first you assume it's frictionless, so you don't have to deal with friction. And then you look at it and what is it closest to? It's not really pinned like C is pinned. It really only looks like it's keeping the diagonal piece from, rotating down this way. This way, which means what it's doing is applying a force there, and not a BX/BY kind of thing. It's just a force that's perpendicular to that little, if we had a longitudinal axis here, it's perpendicular to that longitudinal axis. And I have enough dimensions here with A and B given to know how to create a perpendicular force there. So that's the key to this problem. First of all, you would go and find your AX, AY, and EY. Actually, you only need EY, right? Once you know EY, once you know this guy, then you only have 3 unknowns on this piece, and you would just solve for CX and CY. So the solution steps would be, whoops, I actually don't know how to redo that. Well, we'll just erase it. There we go. There we go. Good enough. The solution steps would be take the whole thing, do the summation of moments about A, and that will give you EY. And then you take EY, so that's step 1. Then you take the free body diagram of BCE, you now know EY, and you do summation step 2. Summation of moments about C will give you B. And then step 3, summation of forces in X direction gives you CX. Step 4, summation of forces in Y direction gives you CY. And then step 5, C, the reaction at C, equals square root of CX squared plus CY squared. So this one is a really 2-piece problem, so it looks simple, but there's actually quite a bit going on in it. So it would actually be graded a good bit harder, or at least more points. And this particular problem is, it's all or nothing, so it's just a 6-point problem. But on a current modern exam, this one would have several pieces to it, so that you could get some partial credit off of it. All right, I think that is probably good. If you have any questions, you can email them. You can put them in the Discord, although I haven't seen many people over there. But whichever way, I have gotten more email questions than Discord questions. And you don't have to tell me if you're going to take the 12 o'clock or the 7 o'clock, the noon or the 7 o'clock exam. You do have to tell me if you're not taking the exam Thursday, because that's different, because we have to figure out what are you doing if you're not doing the exam on Thursday. And I'll send out the Zoom links. I'll post the Zoom links for the exams to attend on tomorrow, sometime before the exams are due to take. All right, I will see y'all tomorrow at noon or at 7.